So we need to be able to specify the concentration of a solution, how much solute is dissolved in the solvent. We can use words that are qualitative, like concentrated or dilute, but we also need to quantitate the concentration. There are many different ways that we can specify the concentration. One of them is mass percent. And this goes back to the generalized definition of percent, which is percent equals the part divided by the whole times 100. So mass percent in a solution, we're looking at masses of the different parts. So we're looking at the mass of the solute divided by the total mass of the solution. That's the solute plus the solvent. And we multiply by 100 to make it into a percentage. So we're not dividing by the mass of the solvent, we're dividing by the mass of the entire solution. And there will be a question that tries to trick you with that on the next exam. Okay. So let's do an example here. Calculate the mass percent of a sucrose solution, that's table sugar, containing 11.3 grams of sucrose and 412.1 milliliters of water. Assume the density of water is 1 gram per milliliter. So they're asking for mass percent. The solution has a solute and a solvent. The sucrose is the solute, the one that there's less of, and the water, being the liquid, is definitely the solvent. So to find the percent by mass, we're looking for the percent of sucrose. That's going to be the mass of sucrose, the grams of sucrose, divided by the grams of the entire solution. The part divided by the whole. And we multiply by 100 to make it a percentage. Then we look at our problem and say, well, what information were we given? Well, we're given the mass of sucrose, so that's useful. So we have 11.3 grams of sucrose. That's what we want in the numerator. And we're given 412.1 milliliters of water. What we need down here is the mass of the whole thing. But they didn't give that to us. They gave us the mass of the solute and the volume of the liquid, the solvent. We need to figure out what the entire solution weighs. There's two pieces, there's two parts, the sucrose and the water. So to find the mass of the whole thing, we need to find the mass of each and add them together. We've got the mass of the sucrose, but we've got a volume of water. Density is the conversion factor between mass and volume. So we can take the volume of water, 412.1 milliliters, and we can use the density as a conversion factor. You don't need to remember the equation for density here. You don't need to do any algebra. Just look at the units. So I want milliliters to go away. Milliliters are going to go in the denominator, so they cancel out. I'm trying to find the mass of the water, so I'll multiply by grams. That tells me where to put this number. It's 1 gram for every milliliter. So it's 1.00 grams per milliliter. Now here, if you got it upside down, you wouldn't notice, because multiplying or dividing by 1, you'll get the same answer, but that's not always the case. So 412.1 times 1, 412.1 grams of water. So in our mass percent equation here, in the numerator, we want the mass of sucrose, which was given to us, 11.3 grams. In the denominator, we want the mass of the entire solution. So the grams of solution, and we often abbreviate it that way, SOL apostrophe N, that's going to equal the 11.3 grams of sucrose plus the 412.1 grams of water. We need the whole thing. So 412.1 plus 11.3. 423.4 grams. That's the mass of the solution. So that's what we want to divide by, 423.4 grams of solution. And then multiply by 100 to get the percentage. My numbers here, I've got 3 and 4 significant figures. Now, that number's looking strange to me, but it is what it is. I'm getting 2.66. Did anybody else get that? Okay, thanks. So 2.66, that would be 3 significant figures. Write down 2 extras, and then go back and round that, and so our final answer should be 2.67%. By mass, this solution is 2.67% sucrose. Any questions? Common mistake that students make is they'll take the mass of the solute and just divide by this 412 and get the wrong answer. And there will be a question on the next exam that will try to trick you with that one. I'm just warning you, okay? Any questions? There are lots of other units for concentrations. And the reason there are so many units is because they are useful in different situations. So parts per 100 is actually the same as the percent. Parts per million, abbreviated ppm, would be grams of solute per million grams of solution. Parts per billion is grams of solute per billion grams of solution. Parts per million and parts per billion are very useful when the concentration is much, much smaller. It's nice to have a unit that is similar in size to what you're measuring so that you get reasonable numbers. Numbers like 20 instead of 2 million. Or 10 to the minus 4. Those numbers are awkward to deal with. The mass percent can be used as a conversion factor, as all percentages can. So the percent, like parts per million is per million grams, cent refers to 100. A percentage is how many parts out of 100 parts. If we say that 75% of the kindergarten class is boys, that means that if there were 100 children, 75 would be boys. It does not mean that there's 75 boys in the classroom because there were only 30, right? But it's out of 100. That's what a percentage means. So anytime we see a percentage, we can make that into a conversion factor. So here we have a different mass percent problem. How much sucrose in grams is contained in 355 milliliters of a soft drink? So that's a 12-ounce can. That contains 11.5% sucrose. And here it's telling us to assume a density of 1.04 grams per milliliter. Why is this density different than the density of water? It's a soft drink. It's got other things in it, right? It's got sugar in it. That's the main extra thing. So when you add sugar to the water, the density is going to change. So let's go through this and write down the numbers that might be useful. So we've got 355 milliliters. The 12 ounces, that's an English unit. We don't use those much in science. It's in parentheses. It's just sort of to give you an idea of how large this is. So we'll just ignore that. We're going to ignore this. We don't need that. So we've got 355 milliliters. We've got 11.5% sucrose. And we are given a density 1.04. That's a horizontal fraction, write it vertically, grams divided by milliliters. So percent means per 100. So let's rewrite this. That means 11.5 grams of the solute, sucrose, per 100 grams of the whole thing. So per 100 grams of the solution. That's what percentage is. How many things out of 100 things? Now this ends up being a dimensional analysis problem. So we've got 355 milliliters, we've got 11.5 grams per 100 grams, and we've got 1.04 grams per milliliter. So which is the likely starting number? Just based on looking at the units. It's the one that cannot be used as a conversion factor. Right, the milliliters. This can't be used to convert anything. This is a per relationship. This is per. So those are probably conversion factors. So this is what we're going to start with. And then we have to ask ourselves, what are we trying to figure out? How much sucrose in grams, right? So that's what we're trying to get to over here is grams of sucrose. And then we have to figure out how can we get there. Well, we're going to look at the conversion factors that we have available to us. Sometimes you'll have to go look for other ones, but start with the ones that are given. So here we've got grams of sucrose and grams of solution. Here we have grams and milliliters. And what does that refer to? Milliliters of what? Grams of what? The solution, the soda, right? So let's go ahead and label that. So this is grams of solution per milliliter of solution. And the 355 milliliters that we're starting with, that's milliliters of what? The soft drink, right? The solution. Okay, so labeling all those grams and milliliters and things can help us. So I've got milliliters of solution here. I've got grams of sucrose. So I'm going to look and see if any of these have those units in them. Well, this one has milliliters of solution. And this would allow me to convert to grams of solution. So let's try that. I'm going to go to grams of solution. And then we'll look at this other one that I have and see what that can do. That can go from between grams of solution and grams of sucrose, and that's exactly the remaining transition that I need. So here I've got two steps. So I'm going to start at the bottom here, where there's a little bit of space. 355 milliliters of solution, soda. My path that I wrote down has three arrows, so I'm going to, 2 arrows, I can't even count. 2 arrows, 2 fractions. Milliliters of solution, grams of solution, grams of sucrose. So those are my units. So milliliters of solution, grams of solution, grams of sucrose. The path told me what to write there. I'm going to take the previous unit and write it in the denominator because those need to cancel out. Divide by grams of solution over here, so those cancel out. I let the units tell me what to do. Once I get them all into place, then I pull the numbers in. So here I've got in front of grams of sucrose, I have 11.5 grams, and in front of solution, I have 100. So that's going to go down here, and I'm going to keep the numbers with their units, 11.5 grams of sucrose for 100 grams of solution. Sometimes you'll end up writing that upside down. It all depends on what you're trying to find. And then I have the density, 1.04 grams of solution. So I put 1.04 with the grams of solution per milliliter. That doesn't have a number. If you need a number down there, write 1. My numbers here all have 3 significant figures, so my answer is going to have 3, and that's going to help me know how many to write down. So I do 355 times 1.04 times 11.5 divided by 100 equals And I know that I need 3 significant figures, so I'm going to write down the first 3 digits and then 2 extras, which happens to be all that's left. That's grams of sucrose. And then when I round this, I'm keeping this tenths place, the 4, the next digit's 5, so I need to round up. And this is 42.5 grams of sucrose. So 42 grams of sugar in that can of soda. It's a lot of sugar. Any questions? These sorts of calculations can be useful in everyday life. If you need to figure out the dose of a medicine, you can actually save a lot of money giving your dog or cat flea medicine by buying the little tubes for the really, really big dog and doing a calculation to figure out how much to put on your small cat. Getting the package for the large dog or the cat costs almost the same amount of money, but the large dog one has a lot more medicine in it. You just need to give less. You don't do the whole tube. But if you can do a calculation like this, you can save yourself a lot of money.